Okay, so Eric Stachura is one of the participants in a number of workshops and has authored a number of modeling scenarios for Symbiote, and he's part of that Georgia Atlantic sprawl of the universities and all kinds and highways that you don't want to be on at 5:30 in the afternoon, et cetera, et cetera. And this is work, as I understand it, that he did with his co-partner in bringing a new child into the world recently. And so he can tell us stories about that. But right now, he's going to tell us about the chemical and biomedical applications of differential equations. So, Eric?
Thanks very much, Brian. And actually, I'm really happy to be following the note. I'm going to hit on a lot of the same ideas and concepts. So this is really a good session, back to back. We'll hopefully hammer home some of the same ideas. So I know what I'm going to talk about today is a little bit technical. And so you can just kind of look at the pictures. I have a lot of pictures and let it kind of absorb over you like a sponge, and you're going to see in a few minutes why that's funny, because I'm going to talk about porous media and sponges. And sorry, it's been a day, but I know it's technical, so just bear with me, and I'll hope to hit on some of the same notes and also tell you some interesting applications of differential equations. Okay, so briefly, this is what I want to talk about. So motivation. So teaching differential equations. So I'm at Kennesaw State University. It's perhaps a good idea I should tell you a little bit about us. So we're part of the State University System of Georgia. We're a public institution, about 40,000 some students. And most of my students that I've had in the past at KSU in my differential equations class are not math majors. Many of them are engineering majors. And so I was really happy to see in the last talk the emphasis on technical communication, because this is one of my favorite things to talk about to my students and emphasize is technical communication. So I'm going to share a little bit about that at the end today, where I have students work on problems with the goal of being able to communicate effectively. And in fact, I have students in my differential equations class working on this right now. They have a draft due tonight, so I'm eager to see what kind of things they're producing. So the motivation here is, I know that I have many engineering students in my class. Many of them do not want to see the theoretical abstract equations that can arise in the theory of the second order differential equations. Many of them are interested in seeing how things, in fact, we were talking about this in my breakout session last talk for a few minutes. Many of them are interested in seeing applications to not only the real world, but also to their major, and how they can kind of get their hands on these tools and actually use them practically. So, okay, I was thinking of, instead of teaching classical second order differential equations, how can I have them learn about a problem that they haven't seen before and may not see, but still kind of get interested in it. So what I'm going to talk about is a problem in chemical engineering, and KSU doesn't have a chemical engineering program. So many of the students are mechanical engineers or computer engineers, but there's no chemical engineers. So I know going into this that students are going to be brand new to this subject, and I'm well prepared for this. And so what I do is prepare them by providing a significant amount of scaffolding in the problems that I give them, so that they can work through slowly and go step by step and not be overwhelmed by this brand new subject that they may have not seen before, and kind of shut down. So I hope to avoid the student shutdown at all costs. So that's a little bit of the motivation of why I was interested in doing this. And as Brian said, I was working on this with my wife, who is in industry. She is an engineer. She's a chemical engineer. So she received her PhD in chemical engineering. And these ideas came about one day when we were both studying, finishing up our dissertations. And we decided that I was working on some differential equations things. She was working on some catalysis things for her chemical engineering project. And we thought, there's actually some nice second order differential equations ideas in here. Let's see if we can come up with something concrete and that's approachable by students. And this is what we did. And so at the end today, I'll talk about how I use these problems in class as a class group project. And how, again, I'll emphasize that students are to work through the problems, but not only that, I really want them to be able to communicate what they're doing effectively rather than kind of just throwing down equations and hoping for the best. So I really emphasize the technical communication aspect. And then I'll leave a few minutes at the end for discussion. But okay, I think I already said this, but yeah, so we have a diverse student population at KSU taking differential equations, most of them not math majors, at least not in my class. And so the textbook problems are pretty standard. And so I wanted to go out and kind of think about something new and talk about a subject that they really may not have seen and one that's applicable in industry. So the problem is actually a super classical one in chemical engineering. I didn't know this before, but apparently this is a classical problem in the chemical engineering community. It's to calculate the concentration of some chemical within a catalyst pellet. So these are all words that students might be terrified of when they first see them. But again, I know this going into the game, and I'm prepared with sufficient scaffolding to help them along. And again, lots of pictures like I show you today to kind of ease them into it without just throwing lots of new words at them and letting them go at it. The point here is what they're going to see is instead of the classical look at the characteristic equation and look at the solutions of the second order equation, you may learn the theory in class, but actually many of my students ask me, where does this come up in practice? And so, okay, we're going to see a very concrete second order differential equation, which models something extremely concrete in the engineering community. But mathematically, it's all we're doing is a constant coefficient second order differential equation, which they will have the tools to do once we talk about the topic in class. And so there's also a problem that we made on that's related to biomedical engineering, which is kind of sometimes too much, but sometimes I'll also add this on to the chemical engineering problem, depending on how the students are feeling. The mathematical techniques are pretty much similar for both of them, second order differential equations. So I try to start from the very beginning and give them enough scaffolding and start with just a definition of a catalyst. So I told them, all right, we're going to look at catalysts. What are these things? So catalysts are materials. And along the way, I try to be super concrete, going to the internet and getting data and showing them explicitly, oh, look, these engineering companies, they buy these things, and here you can see the price. So it's extremely concrete, so they can kind of, in some sense, get their hands on the idea. So we start off with just the notion of a catalyst, which is just a material that can accelerate a chemical reaction without being consumed. And so typically, these materials consist of a porous material. And then I get to talking about precious metals and how expensive these things are, and they get interested by the tremendous price that the companies can spend on these precious metals for catalysis. So what I go through the details and show them that catalytic particles, we can call them pellets, and surrounding them, there's a thin gas film that contains a mix of reactants and products. So students may be turned off by the chemistry a little bit here, but I try and be like, all right, don't worry if you haven't taken that much chemistry. We're just going to draw a picture and see mathematically. Let's just draw just a brief picture to see what's kind of going on here. And so that's what I'll do. I just have a three-dimensional picture here. And so we have this little pellet and we have a thin gas film around it. So you don't have to know any sophisticated chemistry here. We just have this thin gas film around this sphere in 3D. And then I say, all right, this is the 3D object, which is kind of hard to visualize. So let's take a two-dimensional slice and have a look at that. Maybe that's a little bit easier to digest, and that'll help us understand the differential equations a little bit. And so we take a two-dimensional slice, we have something that looks like this. And so I draw in the little particles for them to see. So we have reactants and products, and then I'll take some time to talk about the basic chemistry and refer them to their chemistry textbook if they've taken a chemistry class. So a two-dimensional slice will have this gas film, and then inside you have reactants and products. And then you have your catalytic surface, which is going to have pores in there. So you can imagine that some of the particles are going to be going through the pores. And so I take a little bit of time to talk about, and now you understand why my joke was at the beginning, it was funny to be like a sponge because I talk about a porous media a little bit with the students. And so I kind of go and take the time to talk about what a porous medium is. And so give them examples, some familiar examples like rocks, sponges, some biological tissues. And I like to include this picture, which is kind of showing them the voids or the pores that it can exist in a porous medium. So I think I'm going to skip this, actually. This is a little bit too much of a sidebar. So some of my students are come actually interested in doing some research, and I've had a lot of my differential equation students come and do research with me. And some of them are interested in going beyond differential equations and wondering what kind of other equations can you study. And so I give those students an introduction to partial differential equations in this context. And so the natural partial differential equations that arise here is called the porous medium equation. So I'll skip this just because of the time, but essentially we go through a derivation, all very physical along the way, and we derive what is called the porous medium equation, which is a partial differential equation. And then students will look at different types of solutions. Of course, in principle, in general, this is a very difficult equation to solve in whatever sense you may be thinking, but I try and keep it concrete. And so we're going to look for a solution that looks like this, a traveling wave. Traveling wave is a solution that is going to travel like this, and we learn about traveling waves. And so students who are interested in learning about that will take a little bit of PDEs that goes a little bit beyond the ODEs. But okay, back to the main catalysis problem. So if we go back to our 2D slice, we have reactants and products. We talk about diffusion. So we have to have the reactants diffuse through the pores that are going to reach the extremely expensive precious metal atoms down here. And we're going to see later that once reacting, they should come back up through the pores again. So I don't focus too much on the chemical reactions because I tell them this is not a chemistry class, but I give them enough details to get them interested. And so the idea is that if a reaction is to actually occur, the reactant has to go through the pores. And after the reaction takes place and the product is formed, whatever that may be, the product has to actually transfer back through the pore and then out into the reaction medium that goes through the gas film. So I draw a lot of pictures to help them visualize kind of the chemistry that's going on without going into the chemistry equations. That's beyond what we're interested in. And so apparently a classical problem in chemical engineering is to predict diffusion and reaction in one of these catalyst pellets. And so the idea is to predict the overall reaction rate. And so doing this, we're going to get a second order differential equation, and they'll see by solving that second order equation, they'll solve very concretely this chemical engineering problem. So I give them a result that says conservation of mass. I don't go through the derivation. It's a little bit too technical, and I refer them to a reference if they're interested. But we're going to essentially start from a conservation of mass and get a second order differential equation that way. So the conservation of mass gives us, for the value C, the concentration, gives us a following second order differential equation. And so I pop this thing up and they look at all these letters and are nervous by seeing all these unfamiliar things. But then we go through carefully what exactly is going on. And I say, we've studied differential equations, but I haven't really said where we're studying them. We're kind of just solving them in the ambient Euclidean space. But actually now we have a very concrete problem. I want to solve it in this spherical thing, or if I want to do this in 2D, a circular thing. So in calculus, you may have seen polar coordinates. So that I talk a little bit about polar coordinates, and we talk about the radial equation. You'll see this is coming essentially the radial part of Laplacian. But we don't get too bogged down into the details, and we go through and see this is just a number, K is just a number. We have d by dr of something, and if you work out the derivatives with the product rule, you see this is just a second order differential equation for the function c of r. And this is a familiar thing that they have seen. You've seen second order differential equations, just of new context, a new problem, but you've seen the structure and you should be familiar with the ideas of, oh, second order equation, I should think about characteristic equation and then go from there. We spend some time talking about the nonlinear right-hand side, which can get apparently quite complicated quite fast, but we either take this to be 0 or something similar that makes the differential equation easy to solve. And then we talk about, all right, we've also talked about initial value problems, but we can also talk about boundary value problems and boundary conditions and talk about the physical nature I won't go through it now, but we can talk about, oh, this is a Neumann boundary value problem. We're just prescribing the derivative on the boundary and seeing, instead of prescribing initial data, what I'm doing is prescribing something on the boundary instead. So we'll discuss initial versus boundary value problems there. Now is where I go to the internet and then the textbooks and show them very concretely and how expensive these things are. So, all right, we're going to go pretend that we're in an actual lab and we want to look at the catalytic reaction, which is known as dehydrogenation of cyclohexane. And again, you see these long words and you get stressed out, and I say, okay, don't stress out. We're going to draw pictures and we're going to Google these things and see what this thing is. And if you've taken organic chemistry, great, you may have seen this thing. If not, don't worry about it. And so I give them just from industry, and this is what my wife was telling me, that the process requires something that the engineers call gamma alumina. I had never heard of this before, but you can look it up. And this is a concrete catalyst pellet that has a spherical shape, just like this picture that we're looking at. And then we start putting concrete numbers to make the differential equation more approachable. So we can say that this thing has a diameter of 5 millimeters. And what's our precious and very, very expensive metal? They're always keen on how expensive these things are. What is often used actually in practice, I was actually kind of surprised by this, is they use platinum, extraordinarily expensive, but this is what is actually used in the catalyzation process. And so we talk about dehydrogenation. It's a long word, but it's essentially, if you break it up, what it means is you're just kind of removing hydrogen in each step, and this is essentially what's going on. So then I talk a little bit about this gamma alumina thing and why it's used. And so apparently it's quite popular due to the structure of this material. It makes it particularly resistant to extreme conditions, which is useful in the lab. So then I throw in this picture. I say, again, if you've taken organic chemistry, great. If you haven't, don't worry about it. We're just going to look at this plus H2 stuff on the end, which is exactly what we were saying. Dehydrogenation, we're getting a hydrogen molecule released at each step of the process. We start out with this thing, which we call cyclohexane, and then we keep adding catalysts, and eventually you get to something else, in this case, benzene, after you've removed a few hydrogens at each step of the process. So then we put some concrete numbers, again, taken from the literature, and this is some of the numbers that are actually used. So apparently they do work at 700K, and you have certain numbers for the constants in our second order differential equation. And so then I say our goal is to calculate the concentration profile of this thing within our pellet. So how do we define concentration profile? Well, the concentration profile is just the concentration inside the pellet divided by concentration at the surface. So if we find these two things, we just divide them and then we're good to go. So now we have to solve our second order differential equation. So by conservation of mass, we just get this this second order differential equation for this variable c after we've just rescaled it a little bit. So these are this number phi and C0, these are constants, and R of C is some reaction. So then I just say, all right, we have a second order equation. Let's use the theory that we learned in class to attack the second order problem to see if we can solve this concretely. Then we talk about various boundary value problems and seeing what the appropriate conditions are. I'm going to just breeze through this. And now we get into the more familiar things that they say. So I give them a hint to say the second order equation might be a little bit complicated, but what if we make a change of variables? We talk about substitution when we talk about Bernoulli equations, for example, in class. What if we make a substitution? So let's try making this substitution. We let Z be C times R. And then with that substitution, they derive the following second order equation. And they say, all right, this is something I can solve. Phi is a number. I know how to solve this second order differential equation. This is more familiar. I'm okay with this. And so the solution is just the sum of exponential functions. And then we go through the appropriate boundary conditions and see what the resulting C has to be. So let's see, we got about 10 minutes left. So I'll just take a few more minutes. So it takes a little bit of work to get here, but once they see this familiar thing, they're like, okay, I see the second order differential equation. This is something more familiar that I've seen in class. I can solve this. And then we go through and I say, just like the Bernoulli equations, once we make the substitution and then solve the equation, we're not done. We have to go back. We have to undo our substitution to go back to the original variables. And so I wrote it as hyperbolic sine, but typically I leave this as exponential functions because not everybody is comfortable or happy to see these complicated trig functions in differential equations. And so the last step is to undo our substitution and solve for the function c. And then I'll graph this because students are like, I don't know what this means. I don't know what this looks like. And so we'll spend some time actually understanding the solution and what it means in terms of the catalyst, and reminding them what it is we were looking for. And this is great that we have a solution of the differential equation, but let's go beyond that. So we have this mathematical thing. Let's interpret it in terms of the context of the original chemical engineering problem to solve their concrete engineering problem. So I think I'll skip this. We also do a biomedical problem, which is called the Hydrogel Model. So this is related to knee joint replacements. And so I just want to show you the second order equation. We get, it's a similar problem, different context. If it's just biomedical engineering instead of chemical engineering, you get a similar second order differential equation, and you have to impose boundary conditions. And instead of a sphere, we're actually on a cylinder this time. But besides that, the theory of second order equations still goes through. All right, so running a little bit low of time. So we talk about the solution. Again, I don't want to end there. I kind of want to spend quite a bit of time with the students actually talking about this thing that they get. Well, okay, it's a formula on a piece of paper, but let's really digest it. What does it mean, and why is it meaningful? And also, where is it valid? You've written this thing down. Does it make sense everywhere? Let's really digest what you found. And we go through some of the variables, and I show them that for some of the variables, it actually doesn't make sense. We get a negative concentration, and we think about this physically, and we realize this doesn't make sense. So for a particular range of the parameter variables, some of the solutions that we get don't make physical sense. So we talk about the distinction between mathematical solutions, which are relevant, and then the physically relevant solutions as well. And so along the way, a lot of it is just dimensional analysis. So I keep them, I try to enforce them along the way to keep working with their units. The units, if they get lost at some point with the complicated differential equation or the new nomenclature, whatever it may be, I say, just keep working with the units, see if things are making sense with the units. This is an important thing to do. All right, so last few minutes. So how do I actually do this? So this is a bit much for a homework assignment or even a day in class. This is a lot of information, and I'm well aware of it. So I want to give them enough time to actually think about this and also work together, not be alone, but actually collaborate. And I was really liking hearing about the interdisciplinary collaborations, because most of the time the students are not the same major, which is great. And I'll talk a little bit in a second. I often do this on purpose to ensure that students of different backgrounds and different majors are working together so they can get different perspectives. So I give them a great deal of time to work through this problem together and to consult with me whenever they need to. So they're put into groups and they come up with a draft. And so I'll collect the drafts to assess mathematically how they're going. And what I do, which was a little bit of work on my end, but worth it, I think, to help them, I provide an extraordinarily detailed rubric of things that they should be thinking about, questions I'm going to ask when I'm reading. So I provide this to them at the outset, so they know the type of questions they should be looking for, they should be thinking about. And I find that giving them this rubric at the beginning is really helpful for them. It provides some structure in writing up their final solutions, which is a couple-page paper, which is aimed at communicating technical information effectively. So this could be upwards of a month and a half or 2 months actually from start to finish between the drafts and the groups working together. So I tell them I don't want them to rush. I want you to have time to think and discuss with your group and ask me questions. And the point is to not rush through it, but to really kind of digest it and learn a new problem and see a very concrete applicable problem in a area that you may not have thought about before. So the last thing I want to say is about the groups. So at first I struggled forming the groups and seeing the group dynamics working not so great. So I've had quite a bit of discussions with, we have a Center for Excellence in Teaching and Learning at KSU. I've had quite a bit of discussions with some of the fantastic faculty there about effective group work. And so what I do is I have students grade themselves and their group, and I incorporate that into their final grade. So I find that it's, since I've been doing this, I find that students have an increased sense of accountability on their own sense, since they know that others will be grading them besides me. And I went through a rabbit hole of, there's a whole education literature on building effective rubrics and group work assessments and forming groups effectively. And so all of this to say is I ended up with a very short questionnaire that I can give students at the beginning of the semester. And from that information, I can learn about the students and form groups in a more effective way. When I first started this, I would just kind of say, go work, good luck, and hopefully you guys do well. But I found that the more structure that I provide, especially with the groups and knowing their diverse backgrounds, it has really paid off, and that they've been coming up with some great ideas. And so my plan is to keep doing this structured group work, and especially the rubrics. They really seem to like that. Again, it was a little bit of work on my end, but totally worth it. It guides them. This is in addition to the scaffolding I provide with the problem. So the rubrics, I'm kind of aiming at very specific questions. Some things like, okay, suppose you solve the second order differential equation numerically instead of analytically. What kind of numerical methods have we seen in class that might be applicable to this? Could you try an example on yourself? So I provide them very concrete questions that they should think about or answer either directly or think about themselves to add into their final project. So this is typically how I give them these problems. And so far, I've had pretty good success since I've been adding the rubrics and the structured groups. So with that, I think that's enough technical information for one night. So I'll stop here and say thank you very much for your attention.
Thank you, Eric. Any immediate questions, or I know we all want to see how a rubric works on a problem. Are they uniquely designed for each problem then, I take it?
In principle, yes.
Yes. Okay.
So I will say that, yes. In principle, yes. Depends on how much I can do, but yeah.
Okay. We do have Mark Nelson from Australia saying, do you use Fogler's elements of chemical reaction engineering as a text, I guess?
The title sounds familiar. I don't know if this was the exact book, but this is one of, we use a fundamental chemical engineering book, and this might be the one.
Okay. You mean they do outside when they're, oh no, you use it to reference the problem.
For the data, and they have lots of graphs. Yeah.
Okay.
Eric, thank you for the great presentation. There's a quick question. The rubric idea was great. It seems to be you have a detailed rubric. Is there a sample rubric which would be available somewhere? We can find it, or
I can share it to you. Yeah,
that's amazing.
I just give it to my students, but I'm happy to share it with you. Yeah, I mean, ultimately, the once I give them the project, it's like 5 or 6 pages, but 2 or 3 of those pages are the rubric itself.
Wow.
And so it's extremely detailed. And so they know from the get-go what I'm expecting, what they should be thinking about. And so it's taken me some time to build it, but I think it's a worthwhile thing to include, and especially giving them at the beginning, not at the end. I learned that the hard way. So giving them at the beginning, I think, so they already know cards on the table. This is kind of where we're going. This is what you're going to do. And you can see, and you'll have 2 months. This is a lot of information, but it's all kind of there to help guide you, not to overwhelm you. But yes, if you send me an email, I'm happy to share you a sample rubric. Yeah.
Are they working on other things in class while this is going on, right? Because 2 months is a big chunk of the semester. Right?
Yeah, sure. We'll spend some time in class though discussing it as well.
Okay.
So for different problems, I have some different PowerPoint presentations to spend a few minutes on class. So typically I only do 1, maybe 2 of these projects per semester. This one is really quite involved. There are other less involved ones, but I've only done a maximum of 2 per semester. Otherwise, I find it gets time consuming both for me and the students. especially because I have to devote a little bit of class time to talking about the problems, and time is precious, as you know.
Victoria asks, have you tried to solve PDEs using self-similarity with your students?
This is pretty advanced. I
Okay.
haven't tried it. So what we've tried is just basic traveling waves is one that we've done pretty frequently. But yeah, so, and it's just for this example, porous medium equation. I think that's an interesting idea, though, to try with some students.
One of the things we heard was words like change of variables and keep track of units. And in traditional differential equation courses, we don't hear that much. We do change some variables, but we're never really conscious of units. And of course, units can get you in real trouble when you're adding volts and amps and watts.
Exactly.
You know, of course, when you have chemical engineers in general, they're very conscious of units.
Sure.
If they're not, they blow up the spaceship that they're trying to get up. And so it was nice to hear those words. And you said that you don't always get a problem that they all know about. Indeed, chemical engineering, you indicated most of them mechanical. You didn't have a chemical engineering problem. And yet
Exactly.
these fundamental principles are still taught in their engineering science courses. So you can appeal to them, right? And,
Exactly.
Okay.
Yeah.
Okay.
Yep, exactly. And so I say the units you should be familiar with in your other classes. So you maybe not seen it in a math class before, but in problems like this with unfamiliar variables, unfamiliar data, it's extremely helpful to keep track of the units at each step of the problem.
Okay.
So Eric, sorry, I had a question, but first, thanks so much for the presentation. My question is kind of on the self-grading, you know, that I particularly don't like grading projects. I feel like I'm throwing darts at the wall. You know, one kind of looks better than the other, but what really is the best project? Yeah. And so I love this idea of self-grading, but I feel like if I were a student, I would just like give myself a half-letter grade that I already had, better than I already had in the class, and hope the teacher accepted it. And then I guess the other kind of pedagogical side is like, how do you continue student development? You know, you're the expert here that would know how to do the writing. So I feel like there has to be at least some feedback from you to kind of build them as technical writers.
Yeah, so
thank you.
So let me answer in reverse. So that's why I give them drafts, and usually I just ask for one official one, but I edit as many as they are happy to give me. And luckily my classes aren't too big that I can somehow find the time to go through and look at the drafts pretty carefully and comment on them and give them direction on you should not just be throwing this equation on there. I have no idea what this means. Where's the pros? And so I can see some, since I do 2 of these during the semester, I can see some growth in between the 2 projects of the students. So that's one way that I can see the growth, by giving feedback from the first one and then looking at the result in the second one. And now the self-grading, I totally understand. So I've spent a lot of time digging through the education literature and talking with our CEDL, our Center for Excellence in Teaching and Learning faculty, having consultations with them about group work and self-grading. And after all of this, what I have is just a simple form, and they can rate themselves and each other on a scale. It's not even numbers, it's words. So it's like excellent, very good, good. And I have a scale of translating these words into a point percentage, which I can add or subtract from their total overall grade. So it's a little bit of a convoluted way to do it. And at first it took me a while, but now that I have kind of the hang of it, I can go quickly between the words that they rate themselves and each other. So they don't really even see numbers at all in the rubric. They're just kind of, I say excellent means this, very good means this, good means this, poor means this. And so they give these ratings to themselves and each other. These ratings translate to a point percentage that I have on the back end, and then I turn that into, adjust that into their grade at the end.
Okay. Well,
great. Thank you. Oh, if you need to end now, that's fine. Sorry.
Well, if you have another question, there's no program after this. So if you want to linger, that's fine. It says we have student poster projects, but there are none this evening. There's only one later on. So if you want to ask more questions, please do, if Eric is willing to answer.
Sure, I'm happy to. I don't necessarily claim that I'll have the answer, but I can.
Right. So then you're open to giving like different grades to different students inside the same group?
They most of the time they have different grades. Yeah.
Okay. And then is that like based on individual effort? I feel like if the best student is going to call the project the worst and the worst student is going to call them, right? Like if I'm a bad student, I'm going to be like, oh, this is the best work I've ever done. Look at all that what these other people helped out. Whereas like
it's pretty easy to spot. Yeah.
Right.
Yeah, but
okay.
yeah, you're right. Yeah.
Yeah. I mean, I don't know. I definitely don't have the right answer there, but I really do see that as like a both time saver on my side and like self-reflection on their side in terms of what they did.
Exactly.
And, I could really see some usefulness out of that. So thank you.
Sure. And also at the beginning of the semester, I post what is it? Sorry, it's end of a long day. I post the feedback form that they'll be grading each other on. I say, this is what we're going to see in a month or two. I'm giving these to day one, so you can kind of see the type of things that you're going to be grading each other and yourself on, and seeing how that affects your grade. So I've kind of liked the whole cards on the table thing. This is kind of what you're getting into, and I find that students kind of buy in a little bit better knowing all the information at the get-go. But yeah, that I provide that feedback form, that grading rubric, also just even before the project at the beginning of the semester.
So Victoria was wondering, though, is R times P the size of the pore in your radius change?
Yes.
Okay. Two things. Picking groups is an art form, and you can do it in lots and lots of ways.
Yes.
And also telling them they know what the currency is. The currency is the grade, and telling them a path to the currency. Some people don't like doing that, but I think what you're offering your students is freedom, certainly, to design to meet that. You're not saying it has to be 1.8 inches by, you're not doing that. Yeah. And they're going to be grateful for that. And then when they look at their score and it's on that rubric, they're going to go, yep, I didn't address what if, or exactly. I ignored friction entirely, and I said I was going to come back. I didn't do that. One time I grouped students in a final exam. I threw them in a room for 3 hours, and I put each group of 3 in a room, and I grouped them worst to best. So I put the 3 lowest students together, and they didn't know this. They wanted to know how I was going to pick them, and I told them randomly. Well, I lied. And Tom, who's online, knows I shouldn't have done that because I was at West Point where he was. But at any rate, all the 3 worst students looked at each other and go, there's no Alan here to do it for us. We got to dive in. And they really did. They're capable, but if they've got a superstar in their group, they're also capable of going, well, let Alan do it. And by the way, Alan doesn't want to let them do it because his grade's going to look bad.
Yeah.
So, and the thoroughbreds at the top really raced along. And I found there was no inequity in doing it. But everybody has their own philosophy on groups. It's just...
I'm certainly not claiming mine is the right way by far. This is just the way that I found that happens to work well with my students. You're right. There's such a rabbit hole that I went into of trying to figure out how do I group these students in the most effective way. And it's probably not the most effective way what I'm using, but it's a way that seems to work at a reasonably well. And for the moment, that seems to be enough for me.
Well, and you're laying your cards out. You're not hiding anything from them. You're saying this is what's going to happen. And by the way, they kind of like knowing what's coming ahead.
Yeah.
Rather than is this guy going to go to the top of the stairs and just turn these over his head and see who lands on the first step, So
exactly. And I thought sending them this big packet of things with the project would be overwhelming, but nobody's ever complained. So the project is the problem is on one page, and then you have this pages and pages of rubrics, and I thought that would be overwhelming. But in fact, it's the opposite. They like to have all of this information. They like to kind of see what is going on. So that was a little bit of a surprise to me.
Yeah, and what you don't know is how they're talking to each other about it, because one of them is saying, look, Marjorie, it says here, he's going to ask us this, so we better answer that. That's an approach. So, well, thank you very much again. We are done with official programs for today. But this platform is on, so if you want to go back to Sakoko and wander the halls, and this is a school day, and as Vinod talked at the beginning of his talk, people are tired, and Eric was pointing that out. And I'm retired, so I can sleep till I want, but I'm tired. And so we will see you back tomorrow when we begin at 1, and have a reasonably good day of interesting, varied programs. And bring your questions and curiosity. And thank you again, all of you. Take care.
Thanks, Brian.
Thank you.
And let me just say, I'll put my email in the chat. I know if you
Oh.
were interested in the rubric or the slides, so I'll put my email in the chat, and you can send me a message, and I'm happy to share the information with you guys.
Okay. I'll leave that on so we.
Or yeah. Thanks, Brian.
It's always interesting to see how many people you can actually find their email at their site, and how many are so institutionally paranoid that they don't want to give you an email. And I understand both ways. So it was nice of you to share that. Okay.
Thanks, Yen Ping. Okay.
All right. Good night now.
Thanks, Brian.